Okay, in today's session, we will continue with the analog modulation. Last session, we have discussed about AM modulation and different forms of AM modulation like DSPSC, SSC, etc. So in this class, we will going to discuss frequency modulation and phase modulation. In the first session, we will discuss frequency modulation and phase modulation. After that, we will discuss modulators, AM modulators and receivers, AM receivers and modulators. So we are starting with the topic angle modulation. Angle modulation is a second type of modulation. We have already discussed the analog AM modulation, which is called the linear modulation. So AM is linear modulation. In this session, we'll start with the angle modulation, which is a non-linear modulation. AM is a linear modulation scheme. In this session, we are discussing FM and PM. Both are collectively called angle modulation. Angle modulation is a type of non-linear modulation. This is a non-linear modulation. Non-linear modulation means linearity principle will not be satisfied. That means if you individually modulate, different modulating signals are used, then the resulting waveform will be a linear combination of individual responses. So in the case of AM, it's a linear modulation scheme in which linearity and superposition principle can be applied. In the case of angle modulation, this principle cannot be applied, so it is called non-linear modulation. Angle modulation is further divided into two different modulation schemes. First one is frequency modulation or FM, and second one is phase modulation. So in this first session, we are going to discuss about angle modulation. So what is frequency modulation? Frequency modulation. In frequency modulation, the frequency of the carrier is varied in proportion with the instantaneous amplitude of the message signal. So carrier frequency is varied in proportion with the message signal in FM system. Okay. So frequency is made proportion with the message signal, which is denoted as M of t. Message is denoted as M of t. So frequency of the carrier, which is a constant value Fc, then this constant value is varied in accordance with the message signal. So instantaneous frequency will not be a constant value. It can be written as Fc plus some deviation from this frequency, that is carrier frequency, and that is usually denoted as Kf into M of t. Okay. Okay, amplitude of, yes, right. That is, frequency is varied in proportion with the amplitude of the message signal. Okay, instantaneous value of the message signal. Okay, so M of t is magnitude of the message signal at any instant of time t. So Kf is called the frequency sensitivity of the modulator, is called the frequency sensitivity of the modulator, of FM modulator. And second type of angle modulation is phase modulation or PM. In this, the phase of the carrier phase, usually denoted as phi, carrier phase phi, is made proportion with the instantaneous value of the message signal. So phi can be written as Kp into M of t. Proportionality constant is taken as Kp. So phi of t, instantaneous phase of the message signal. Sometimes it is denoted as phi I. Instantaneous phase is denoted as phi I of t, which is written as Kp into M of t. So quantities that are varied in FM and PM are different. Okay. In first case, frequency of the carrier, which is constant otherwise, because we are using a single sinusoidal wave as a carrier, and its frequency is fixed. Its value is Fc. But in FM system, this frequency is made to vary in accordance with the instantaneous value of the message signal. In second case, the quantity that we are varying is phase of the carrier signal. Carrier phase is varied in proportion with the instantaneous value of the message signal. So we got two different equations. Basic equations are different for FM and PM. Even though they have similar characteristics, their basic definition is different. Okay, we will discuss about similarities and difference of FM and PM. So we'll move on to second slide. Here, FM and PM waveforms are given for a given modulating wave. First figure indicate carrier wave. I think picture is clear for you, all of you. Image is clear. Is it clear? Okay. Right. Okay. Thank you. First figure is carrier wave whose frequency is fixed. What is frequency of carrier wave? Fc. You can see the time period of the waveform is uniform. Therefore, the frequency of the carrier wave is fixed and is given by denoted as Fc. Now, second figure indicates modulating waveform. So, modulating waveform is given in bold curve, okay, bold line. So, this is modulating signal. Two waveforms are shown. Modulating signal is a sinusoidal wave. This one is AM sine 2 pi FMT. Modulating signal is a sinusoidal wave. If we differentiate this signal, we will get a cosine wave. So cosine wave is m dm by dt, derivative of actual message signal. So when we differentiate a sinusoidal signal, we will get a cosine waveform. So dm of t by dt is a cosine waveform, and its amplitude will be different. It is a cosine waveform anyway. It is a cosine waveform. Amplitude will be 2 pi fm into am. Okay, right? If we differentiate this, we will get a cosine waveform. So in FM system, the frequency is made in proportion with the instantaneous amplitude of the message signal, that is AM sine 2 pi FMT. Here sine AM sine 2 pi FMT is the modulating signal. So modulating signal is having value 0 at this point. At t equal to 0, its value equal to 0. Its value increases with the time and it becomes peak value at this point. Okay, at this point it is having peak value. So the frequency of FM signal has peak value at the highest value of the modulating signal. When modulating signal is having highest value, that is AM, frequency is maximum. Okay, so there is a deviation in frequency from normal value, that is Fc. It varies from normal value Fc to peak value. Then as modulating signal decreases, what happens to the frequency of FM wave? As amplitude of the modulating wave decreases, frequency of the modulated wave, FM modulated wave decreases. And you can see the lowest frequency at the lowest value of the modulating signal, that is at this point, where modulating signal amplitude is minus AM and corresponding frequency is the lowest value. Okay, so you can see a frequency deviation from this point to this point. Here frequency is maximum and that is denoted as Fc plus delta Fc, and here frequency is minimum, that is Fc minus delta Fc. Okay, so frequency is varying continuously with the respect to the instantaneous amplitude of the modulating signal. Okay, so this is the variation of frequency in one cycle. The variation will be repeated in the other cycle also. Okay, is it clear? You can see the frequency variation from this figure, which is maximum when modulating signal is maximum and minimum when modulating signal is minimum. And the deviation, peak deviation, is denoted as delta f. Delta f is frequency peak frequency deviation. Frequency deviation. Clear? Delta f means peak frequency deviation, that is the maximum frequency deviation from its center value, that is fc. Okay, so when you plot frequency of fm wave, it is having maximum value, that is fc plus delta f, fc plus delta f, and a minimum value fc minus delta f. So the deviation both sides is delta f. Delta f is the maximum frequency deviation. In a PM wave also you can see the frequency variation, frequency deviation from fc, but it will be in another form, because in PM wave frequency deviation occur when derivative of message signal is maximum. When derivative of message signal is maximum, frequency deviation become maximum value. Okay, so you can see maximum frequency at t equal to 0, where derivative of modulating signal is maximum, which is cosine wave. Cosine wave is having peak value at t equal to 0. So PM wave is having maximum frequency at t equal to 0. So only difference is that frequency variation is occurring in a different way. When you compare FM wave and PM wave, frequency deviation will occur in a different way. That's the only difference. But the amplitude of the FM wave or PM wave remains a constant value. That is denoted as AC. Amplitude of FM and PM remains constant value. Only changing parameter is frequency in the case of FM wave and phase in the case of PM wave, as far as modulating signal is concerned. When we compare with the modulating signal, frequency variation will occur in proportion with the modulating signal in the case of FM, and for PM, phase deviation will occur in proportion with the modulating signal. Right? In both cases, we'll observe that there will be frequency change, because rate of change of phase is called a frequency. So when phase changes, there will be a change in frequency also. So I think the figure is clear for you. Let's move on to next topic. Now we are going to discuss frequency modulation in detail. So in frequency modulation, basic modulation is the way in which the frequency of the carrier is varied in accordance with the instantaneous amplitude of the modulating signal. As I have already written the instantaneous frequency of the modulated wave, let us start with the carrier wave, carrier signal. Carrier signal is denoted as C of t, which can be written as AC cos or sine. I can use cos 2 pi fct. So this is instantaneous value of the carrier waveform. Now carrier frequency is fc, but frequency of FM signal is fi equal to fc plus kf into m of t. The parameter kf is frequency sensitivity of the modulator. So this is an important equation for FM. And the frequency varies. If m of t is a single tone frequency, if we consider modulating signal as a single frequency signal, let us consider m of t as am sine or cos 2 pi fct cos 2 pi fmt. Okay, right? Is am cos 2 pi fmt. Okay, then Fi can be written as Fi, instantaneous frequency of Fm modulated signal, equal to Fc plus Kf into Am into cos 2 pi Fmt. Fm is the frequency of modulating signal. So we are considering a single tone case, single frequency case, single tone modulating signal. In actual situation, a modulating signal consists of different frequency components, but in analysis we'll take only single frequency component because of mathematical simplicity. So Fi equal to Fc plus Kf into Am cos 2 pi Fmt. So what will be the peak value or maximum value of deviation? So this term is called a deviation. Peak deviation will be equal to Kf into Am, because cos 2 pi Fmt is having maximum value equal to unity. So this quantity is having maximum value. So maximum value of cosine function is 1. Okay. So this quantity is 1. So peak deviation is delta f. So Fc plus delta f into cos 2 pi Fmt. So this is equation of Fm frequency, instantaneous frequency of the Fm signal. Okay. So this is an important equation for Fm signal. So these equations are given here. Fi, instantaneous frequency of Fm wave, instantaneous frequency. Okay, Fc carrier frequency. Fc is carrier frequency. Parameter Kf is frequency sensitivity. Single tone, we are considering single tone modulation only because of mathematical simplicity. So otherwise, if we consider a multi-tone signal, it will be called quite complicated. Mathematically, it will be quite complicated. So we'll consider single tone modulation for analysis purpose. Okay. Modulation index, all other quantities are defined with the single tone case because of mathematical simplicity. So Kf is frequency sensitivity. And m of t is modulating signal. Yes, due to single tone, single frequency. Yes, single tone means single frequency component. So we'll consider only one frequency component. That is, m of t is taken as a pure sinusoidal wave. So in that case, we can calculate the deviation and also the modulation index very easily. Okay. Right. M of t is modulating signal. Modulating signal. Now, this equation gives instantaneous frequency of the Fm signal, and Fm signal as a function of modulating signal is given as Fm signal is S of t equal to AC cos 2 pi Fct plus 2 pi into Km integral of m of t dt. So this term depends on modulating signal. Okay, so the frequency of the signal will be equal to Fi, which is equal to Fc plus Kf into m of t. So you should note this equation S of t. So this equation is a general equation. in singleton case, we can substitute m of t equal to am cos 2 pi fmt to obtain the expression. So only this expression is required. FM signal is having a constant amplitude. So amplitude of AM signal is a constant value. So amplitude of AM is equal to amplitude of the carrier wave, but the frequency is varied. So amplitude remains a constant value, but frequency is varied in accordance with the instantaneous value of the message signal. So this is the equation of FM signal. Okay, I think it is clear. Let us move on to next slide. Next, modulation index. Beta denotes modulation integral term. Okay, right. Integral term will be obtained when we take instantaneous phase. Actually, you don't require all the derivations. That is why I'm skipping those derivation, mathematical derivation. And since you are asked this question, I will do the required. I'll give the required expressions. Actually, S of t is written as AC cos theta e of t. Theta e of t is called instantaneous angle, phase angle. Okay, theta e of t will be instantaneous phase angle, and instantaneous phase angle theta e of t will be obtained as 2 pi. Actually, phase and frequency are related. What is this quantity? Theta e of t is phase angle. Phase angle will be obtained from frequency by integrating frequency, because phase angle frequency is derivative of phase angle. That is, relationship is instantaneous frequency equal to 1 by 2 pi into 1 by 2 pi into derivative of theta e of t. That means theta I of t equal to 2 pi into integral of fi dt. Okay, theta is instantaneous phase angle, and that will be obtained by integrating fi dt and then multiplying with the 2 pi. So this will give 2 pi into integral of fi. For fm, it is fc plus kf into m of t. When you substitute this term here, we'll get the two terms. Fc is a constant value, isn't it? What is the integral of constant term? Integral of constant term. Are you familiar with integration? Integral of constant term will give t. So first term will be 2 pi into fct plus kf is a constant value, which is frequency sensitivity of the modulator. So 2 pi kf is a constant value, and remaining term is integral m of t dt. Okay. So this is expression for instantaneous phase angle of the angle modulated signal. So when we substitute theta I of t, we'll get this expression AC cos 2 pi fct plus 2 pi kf into integral m of t dt. Saurabh, is it clear? Is it clear for all of you? Simple mathematics is applied. Okay. So that is why I am not doing this type of simplification. It is not required for you. Next quantity is modulation index. The modulation index beta is defined as maximum, is a ratio of maximum or peak deviation to modulating signal frequency. That is, beta is defined as peak deviation. Peak frequency deviation divided by frequency of modulating signal. So beta is modulation index and is given by delta f divided by f of. Delta f divided by f of. For delta f is peak frequency deviation. And peak frequency deviation is given by Kf is frequency sensitivity. Okay. So I will derive the equation delta instantaneous frequency of the modulated signal Fi equal to Fc plus Kf into modulating signal M of t. Okay. This is the equation, basic equation of instantaneous frequency of modulated signal. If you consider single tone modulation, that is M of t equal to Am cos 2 pi fmt, single tone frequency, that is modulating signal is written as Am cos 2 pi fmt, then Fi equal to Fc plus Kf into Am into cos 2 pi fmt, right? So what is peak deviation? Delta f equal to Kf into Am. So delta f, that is peak frequency deviation, is given by Kf into Am. So when you write delta f equal to Kf into Am, we'll get beta equal to Kf into Am divided by Fm. So Kf is frequency sensitivity of the modulator. Let us take an example. If you consider a commercial broadcast with a maximum frequency of modulating signal, which is 15 kilohertz. In commercial FM broadcast, maximum frequency, modulating frequency is 15 kilohertz. And deviation is 75 kilohertz. Deviation is 75 kilohertz. So what will be modulation index? Can you find modulation index? If FM modulating frequency is 15 kilohertz? Yes. Chetana, right answer. Yes, it is obtained by taking the ratio of frequency deviation delta f divided by modulating frequency FM. That is 75 kilohertz divided by 15 kilohertz. So we'll get 5. Okay. If modulating frequency, yes, voice is not clear. Okay, I will check. I'll try to make it clear. Okay, try now. How is audio? How is audio? Okay, right. Thank you. So beta, if you calculate beta for different value of FM, if FM equal to 5 kilohertz and peak deviation delta f remains, peak deviation delta f remains the same value 10 kilohertz. Okay, if peak deviation remains same value, then we'll get the modulation index beta equal to in this case delta f divided by FM. What is the value? 75 divided by 5. 75 by 5. What is the value? Yes, it will be 15. 15. So in this case, modulation index depends on frequency of the modulating signal. So modulating signal frequency has a role on determining modulation index. Further, modulation index in FM can be greater than 1. Usually for commercial broadcast, it is taken usually greater than 1, greater than 5. It is usually greater than 5. So beta can be greater than 1 in the case of FM signal. But in the case of AM, beta should always, or modulation index is always less than or equal to 1. Maximum modulation possible is 100% modulation. In that case, modulation index become unity in the case of AM, but in the case of FM, beta can be greater than unity. Okay, in practical purpose, practical broadcasting purpose, beta is always greater than unity. So I think this equation is clear for you. Modulation index, very important equation. Okay, this is a very important equation. Beta equal to delta F by FM. I will move on to different types of FM signals. FM can be divided into two types of schemes. First one is narrowband FM. Narrowband FM, as the name indicates, narrowband FM is having lower bandwidth, lesser bandwidth. And second one is wideband FM, where bandwidth of FM is much greater. So based on the value of modulation index. So modulation index determines the bandwidth of the FM signal. Therefore, for narrowband FM, beta is very small value. Okay, beta is usually less than 1 for narrowband FM. So in the case of narrowband FM, the bandwidth is small, beta is small, and the spectrum consists of the carrier and the two sidebands, the upper sideband and the lower sideband. You can compare this with the AM. It is just like AM signal with only two sidebands, the upper and lower sidebands. So it consists of carrier, upper sideband and lower sideband. So narrowband FM is a modulation scheme, FM modulation scheme in which F beta is smaller than unity. So this is used since its bandwidth is very small. Only 2 FM is the bandwidth. So bandwidth can be calculated. It is equal to bandwidth of AM, which is equal to 2 into FM. 2 FM is the bandwidth of the narrowband FM. So it is mostly used in mobile communications such as police wireless, ambulance, taxi cabs, etc. So in wireless sets, this type of narrowband FM is used because of narrow bandwidth and power. Power is effectively used as compared with the AM. Okay, efficient use of power is taking place in FM as compared with the AM. Therefore, in this type of mobile communication systems, narrowband FM is used. Okay, I think it is clear. Beta is less than 1 is the property. Bandwidth of narrowband FM is 2 FM. Then applications are mobile applications such as police wireless, ambulance, taxi cab, etc. Let us discuss about wideband FM. Commercial FM is wideband FM. Commercial application, commercial broadcast applications will use wideband FM. So what are features of wideband FM? First one, the frequency modulation. This frequency modulation has infinite bandwidth. So ideally, there are infinite number of sidebands. Infinite bandwidth means infinite number of sidebands. Sidebands are frequencies above and below carrier frequency. If we consider carrier frequency, this component will be present. Okay, then first side frequency is FC plus FM. Second one is FC plus 2 FM, and so on. Similarly, there will be lower sidebands like FC minus FM, FC minus 2 FM, etc. Okay, so in wideband FM, there will be infinite number of sidebands. So the bandwidth of wideband FM is infinity. Ideally, it is infinity. Practically, we'll use a formula for calculating bandwidth of wideband FM. Second feature is modulation index, which is very large, larger than unity. So beta is greater than unity. You can take beta greater than 1. Third property, spectrum consists of a carrier and infinite number of sidebands which are located around it. Okay. So upper sidebands are located above FC, lower sidebands are located below FC. So there will be infinite number of sidebands. That is why its bandwidth is infinity, ideal case. This is used in entertainment, broadcasting applications such as FM radio. In TV, we'll use FM for modulating sound. Modulating sound. And picture information is modulated using vestigial sideband modulation, VSB, in TV. VSB is used for picture modulation. Both video and sound are transmitted in TV. Video information or picture informations are modulated using vestigial sideband transmission. Vestigial sideband. And sound is transmitted with this modulation, FM modulation. So FM is used for modulating sound waves in television transmission. So these are applications of wideband FM. So for wideband FM, frequency modulation has infinite bandwidth. Second characteristics is modulation index is large. Third one, spectrum consists of a carrier and an infinite number of sidebands. Fourth one, they are used extensively in entertainment broadcasting applications. So let us move on to next topic, which is phase modulation. Phase modulation. VSB is a kind of AM. VSB is a kind of AM, not FM. VSB is a type of AM modulation. VSB is a type of AM modulation. It has frequency components, carrier frequency components, plus a complete sideband, USB or LSB, plus a portion of other sideband, unwanted sideband. That means it consists of carrier, one full sideband, whether it may be bandwidth formula for wideband FM that we will discuss. Bandwidth, I will give you the expression for bandwidth that we will discuss after FM, because both FM and wideband, both the PM and wideband FM have same expression for bandwidth. So we'll discuss that after discussing PM. Vestigial sideband modulation consists of carrier wave, one complete sideband, and a portion of unwanted sideband. If we are transmitting a USB, a portion of LSB is also transmitted. Okay. That is a type of AM modulation. Next, we move on to phase modulation, PM. In frequency modulation, the frequency of the carrier wave varies. But in phase modulation, the phase of the carrier signal varies in accordance with the instantaneous value of or amplitude of the modulating signal. Here, carrier phase, if carrier signal C of t is given as cos 2 pi fct plus phi, phi is the phase angle. And in this case, in this modulation scheme, this phase angle phi is made in proportion with the modulating signal. So phase angle is proportional to m of t. So phi can be written as kp into m of t. So instantaneous phase of the carrier is made to vary in proportion with the modulating signal. Therefore, expression for PM signal will be PM wave can obtain expression by substituting phi equal to Kp into m of t. So AC into cos 2 pi FCT plus Kp into m of t. If we compare this equation with the FM wave, for FM wave, signal S of t equal to AC cos 2 pi FCT, so FCT plus 2 pi into Kf into integral m of t dt. Can see the difference and similarities between FM and PM wave. In PM wave, phase is proportional to modulating signal. In FM wave, phase is proportional to integral of modulating wave. In FM wave, frequency phase is instantaneous phase is proportional to integral of the modulating signal. So that is the difference. So you should not write down this equation S of t expression for PM wave, which is given by AC cos 2 pi FCT plus Kp into m of t. Right? You can see the difference between PM and FM wave. Next, instantaneous phase. So Kp is phase sensitivity of PM modulator. Kp is phase sensitivity of PM modulator. Modulating signal is m of t. If you consider single tone case, m of t can be written as am cos 2 pi fmt. Modulating signal is taken as a single tone signal. In that case, phi I equal to Kp into am into cos 2 pi fmt. S of t, the signal, PM signal, is S of t equal to AC cos 2 pi FCT plus Kp into m of t. AC is amplitude of the PM wave, which is a constant. Amplitude of PM wave remains a constant value, but phase is made proportion with the modulating signal. So these are equations related to PM wave. You can note down this equation for instantaneous phase of the phase modulated signal, phi of t equal to Kp into am cos 2 pi fmt for single tone case. Now coming to modulation index. Modulation index is defined as maximum phase deviation. So PM modulation, beta is defined as maximum value of phase deviation. Maximum phase deviation. Phi I is given by Kp into m of t. So maximum phase deviation will occur when m of t is maximum. M of t is taken as a single tone signal, am cos 2 pi fmt, this is single tone signal, modulating signal. The maximum value phase deviation delta phi will be equal to Kp into am. That is the maximum. Am is the maximum value of modulating signal. So delta phi equal to Kp into am. So phi is maximum phase deviation and is given by Kp, delta phi equal to Kp into am. So beta modulation index of PM wave beta equal to maximum value of phase deviation, which is given by Kp into AM. So modulation index depends on amplitude of the modulating signal, but does not depend on frequency of the modulating signal. In FM signal, beta was defined as frequency deviation by FM, which is given by Kf into AM divided by FM. So in this case, in the case of FM, modulation index depends on amplitude of the modulating signal as well as the modulating signal frequency. So these two quantities determine the value of modulation index in the case of FM. But in the case of PM, it is independent of modulation index is independent of FM, frequency of the modulating signal. So that is only difference between modulation index of FM and PM. Okay, I think it is clear for you. All of these expressions are important. Beta for FM and beta for PM. Okay. Thank you, Suraj. Okay, let us move on to important topic, bandwidth of FM and PM. So both FM and PM have same expression for bandwidth. Okay. For narrowband FM, bandwidth is already obtained. Bandwidth for narrowband FM. Narrowband FM. This is 2FM equal to bandwidth of AM signal. But for wideband FM or PM, wideband FM or PM, we will use another formula given by Carson's rule. Carson's rule gives an empirical formula for calculating the bandwidth of wideband FM or PM. So for calculating the bandwidth, we'll consider the number of significant sidebands, that is number of significant sidebands where most of the power is focused or concentrated. Number of significant sidebands is taken as beta plus 1. Okay, we'll consider number of sidebands as beta plus 1. Number of sidebands is taken as beta plus 1. So bandwidth equal to, this is number of significant sidebands, and the spacing of sidebands will be 2FM. Okay, so 2 into beta plus 1 into FM is the expression for bandwidth, where FM is modulating signal frequency, beta is modulation index of the wideband FM or PM system. Okay, so bandwidth depends on modulation index as well as modulating signal frequency. So first term is 2 into beta into FM, 2 into beta into FM plus 2 into FM. We have already obtained a relation that maximum frequency deviation delta F and modulation index is related by the relation delta F by F1 FM equal to beta. So what is frequency deviation delta F? So delta F equal to beta into FM in the case of FM. For FM, signal bandwidth can also be written as 2 into beta into FM is delta F. So 2 into delta F plus 2FM. Another formula is 2 into delta F, frequency deviation plus frequency of the modulating signal. So this is expression, another expression for calculating bandwidth of FM. So this formula can be applied for FM and PM, and this is another formula, 2 into delta F plus FM is the bandwidth. So here we are considering a number of sidebands FC, first sideband is FC plus FM. If we consider only one sideband, we'll have 2 FM, FC minus FM, etc. Beta plus 1 into FM, like this. The number of significant sidebands are considered. And this consideration is based on the fact that most of the power will be concentrated on this sideband. Outside the sideband, power is negligible. Even though there are infinite number of sidebands, the power outside this range, frequency range, is considered negligible. So we'll consider beta plus 1 sidebands, and total bandwidth is obtained as 2 into beta plus 1 into FM. This is Carlson's rule, important rule for calculating the bandwidth of a wideband FM or PM. So you should note these equations. Bandwidth equal to 2 into beta plus 1 into FM. So when you compare the expression of bandwidth of FM, wideband FM, with the bandwidth of AM systems, what is the difference? In this case, in the case of FM or PM system, beta will also determine the value of bandwidth. Okay, so beta bandwidth depends on modulation index also. So as modulation index is more, bandwidth will be more. As an example, let's consider an example with modulating frequency FM equal to 10 kilohertz. If you consider this example with the modulating frequency FM equal to 10 kilohertz and the modulation index equal to beta equal to 7.5. If you consider 7.5 as modulation index, what is bandwidth of FM? Bandwidth of FM. Can you calculate bandwidth of FM with the modulating frequency? Yes. Right. So 85 into 2. Right, Chetna. 2 into 7.5 plus 1. Beta is 7.5 plus 1 into 10. 10 kilohertz. So yes. 170 kilohertz. Yes, that's an important equation. So this is important equation. Okay, it's 170 kilohertz. 85 into 2. We will get the 170 kilohertz. We can also calculate using this formula. What will be frequency deviation in this case? Frequency deviation. We can find frequency deviation from beta and FM. It is equal to 7.5 beta into, what is frequency deviation, beta into FM. Frequency deviation in this case, it is 7.5 into 10. 7.5 into 10, which is given by 75 kilohertz. Frequency deviation is 75 kilohertz. So you can use second formula for calculating bandwidth. Bandwidth equal to 2 into 75 plus 10. 85 into 2 equal to 170 kilohertz. 170 kilohertz. Okay. So this is an important formula. Questions will be asked based on this equation. It will be provided with beta and FM, or sometimes delta F and FM to calculate the bandwidth. So I think this is clear for you. You got the idea? Now power, yes. Okay. Thank you, Chedna. Power of FM and PM signal. FM and PM signals are given by S FM of T. FM signal is given by AC cos 2 pi FCT plus 2 pi KF into integral M of T dt. You know that power of amplitude of FM signal remains a constant value. Amplitude equal to, amplitude is a constant value equal to AC. So power power of FM signal is same as power of carrier wave. AC square by 2. AC square by 2 is power of carrier. So power of FM signal is equal to power of carrier. No change in power. So power remains a constant value as far as amplitude of carrier wave is remains constant value. The AC remains a constant value. The power will be a constant value in the case of FM. But in AM, power depends on modulation index. So in that case, modulation index will determine the power level. But in this case, power is a constant value equal to carrier power. If we consider PM wave, its expression is F PM of t equal to AC cos 2 pi FCT plus Kp into M of t. This is expression for instantaneous value of PM wave. Here also amplitude is a constant value. Amplitude equal to AC. Power of PM signal is also constant value given by carrier power. Actually, carrier power is distributed among different sidebands in FM and PM modulation schemes. Actual power remains a constant value. Power distribution is taking place. Power is distributed among different sidebands. So this is all about power of FM and PM signal. It is determined from the value of AC, that is amplitude of the carrier signal. Okay, if you consider an example with AC, FM signal, FM of t, total power of this signal, 10 cos 2 pi FC is 100t plus 1000t plus 2 pi kf into integral 0 to t m of t dt. If you consider this expression, what is power? No need to calculate any other quantity. You should take amplitude of the carrier wave, which is a constant value. Power P is equal to AC square by 2. AC equal to 10 is 10 square by 2. 10 square by 2 equal to 50 watts. Power is simply calculated using this formula, AC square by 2 for both FM and PM. Okay, now interrelationship of FM and PM modulators. So these two modulators can be used to generate the other waveform. We can use a PM modulator for obtaining FM wave. Similarly, an FM modulator can be used for obtaining a PM wave. So if you use an integrator, this block is an integrator. If you use an integrator before phase modulation, that is, message signals are first integrated. It is converted into integral m of alpha d alpha or m of tau d tau. It is a dummy variable. Okay, so m of t is converted into integral. Then it is phase modulator. We will get a FM signal. Similarly, when you use a differentiator for modulating signal and then a frequency modulator, we will get a PM wave. So PM wave is generated from FM using FM modulator by the use of a differentiator. Abhi, do you have any doubt? Abhi? All right, okay. So when the message signal is first integrated, then phase modulated, we'll get a FM signal, and in second case, modulating signal is first differentiated, then passed through phase modulator, PM modulator will get a PM out. So this is interrelationship of FM and PM modulators. You can compare this block diagram with the equation. Okay, by comparing equation, we'll get same thing. Mathematically can be proved. Now, the difference between frequency modulation and phase modulation. Frequency modulation and phase modulation. What is the similarity and difference between frequency modulation and phase modulation? First point is frequency modulation is proportional to frequency is proportional to frequency is proportional to modulating voltage. In second case, it is phase that is proportional to, I will strike this modulation. Phase is proportional to modulating voltage. In frequency modulation, frequency is proportional to modulating voltage. In phase modulation, phase is proportional to modulating voltage. So that is first point. Second point, associated with the change in frequency, there is some phase change. Okay, in FM system, there is a change in frequency and there will be an associated change in phase. Similarly, an associated change in phase, there is some frequency change. So in both case, phase and frequency are changing, but the way in which they are changing is different. In first case, frequency is changing with the in proportion with the modulating signal. In second case, phase is changing with in proportion with the modulating signal. Third case, it is possible to receive FM on a PM receiver. Okay, both have same characteristics. So we can obtain an FM on PM receiver, but the way modulating signal is recovered will be different. Okay, or the form of modulating recovered signal will be different from actual signal. There will be a differentiation or integration taking place. If it is possible to receive FM signal, FM on PM receiver, so it is also possible to receive PM on FM receiver. Can use PM receiver to receive FM signal, but the final form of modulating signal will be different. Fourth property is noise immunity is better than AM and PM. FM is having the highest noise immunity in analog modulation schemes. So noise immunity is better than AM and PM. When you consider PM wave, noise immunity is better than AM but worse than FM. So noise immunity is better than AM but worse than FM. And fifth point is signal to noise ratio is better than in phase modulation. So S/N ratio is also a measure of signal strength over noise strength. S/N ratio is signal power divided by noise power. Okay, usually expressed in dB. Signal to noise ratio is better than phase modulation. So in PM, in FM system, signal to noise ratio is better than phase modulation. Next, in the case of phase modulation, signal to noise ratio is poor than frequency modulation. So these are comparison of different parameters. Okay. Signal to noise ratio, noise immunity, these are better for FM and comparing with the PM. Next point is frequency modulation is widely used in broadcast, but phase modulation is used in mobile system. Phase modulation is mostly used in mobile communication. Frequency modulation is widely used in broadcast. Next point is in FM, the frequency deviation is proportional to modulating voltage. This thing we have already discussed. In PM, frequency deviation is proportional to modulating voltage as well as modulating frequency. Okay, in this case, frequency deviation is proportional to modulating voltage as well as modulating frequency. Slight difference. And eighth property or characteristics is amplitude of FM wave is constant. For PM wave also amplitude remains a constant value. Ninth property, in FM, received signal is one of highest quality. Okay, received signal is of highest quality because of high noise immunity and high signal to noise ratio. In PM, received signal is of less quality comparing with the FM. Quality is less comparing with the FM. So these are different characteristics and their comparison of PM and FM wave. Please note these points. Let's move on to next topic. Difference between amplitude modulation and frequency modulation. So in amplitude, only amplitude varies. The frequency and phase remains the same. Frequency and phase of the carrier remains the same. Only carrier amplitude is varied. In FM modulation, frequency modulation amplitude remains the same. Frequency and phase will be varied. So in second point is important. Its modulation index varies from 0 to 1. In amplitude modulation, the modulation index varies from 0 to 1. In frequency modulation, its modulation index can be greater than 1. So beta can be greater than 1. It's an important point. Third point is it has only two sidebands. AM has only two sidebands. Frequency modulation, it has infinite number of sidebands. Okay, clear? All these we have discussed earlier. Next point, it has simple circuit. AM has simple transmitter and receiver circuit. For FM, the circuit of transmitter and receiver is complex. AM has simple circuit and FM has complex circuit. Next point is amplitude of the carrier wave is modified. So in order to send the data or information, okay. The carrier amplitude is varied. In this case, carrier frequency is varied. Next point is important. It requires low bandwidth in the range of 10 kilohertz. So for commercial broadcast, AM signal requires less bandwidth. It is about 10 kilohertz. Whereas for FM broadcast, it requires high bandwidth in the range of 200 kilohertz. Okay, almost 20 times greater than the bandwidth of the AM signal. For FM signal, the bandwidth is 200 kilohertz, and for AM signal, it is only 10 kilohertz. So bandwidth of FM is 20 times the bandwidth of AM. Next, in AM, received signal is of low quality. See, because of noise effect, the received signal suffers the most in AM system. But in FM system, received signal of high quality. Okay. That is an important point. Advantage of FM over AM is signal quality is very high. Because of less immune to noise, it is less immune to noise, and also it is having high signal to noise ratio. FM system is having high signal to noise ratio. Next point is also important. Next point is AM works in a frequency range of 535 to 1705 kilohertz. 535 to 1705 kilohertz. This is the frequency range of AM broadcast, And FM broadcast is in the frequency range from 88 to 108. 88 to 108 megahertz. So this is the frequency range of FM broadcast. So compare these two frequencies. You should remember the frequency ranges because it is asked previously in your exam. Next, AM operates in medium frequency, MF and high frequency range. And this FM system operates in VHF range, very high frequency range. That is in megahertz range. This will be hundreds of kilohertz. Frequency range is given. So medium frequency and high frequency range is the operating frequency range of AM. Whereas for FM, it is in megahertz, 88 to 108 megahertz. So it is in VHF range. Next point is it has poor sound quality. AM is having poor sound quality, but FM is having better sound quality. These are few points related to FM and PM broadcast. So with this, we are ending this discussion on FM and PM. Now we are going to discuss few questions that are asked previously in your exams, in LIS exam, that are related to FM and PM. These questions are related to FM and PM. First question. In FM, the carrier frequency deviation is determined by, in FM, you can send your answer. Answer please. In FM, the carrier frequency deviation is determined by option A. Chetna says option A. Sarabh says option B. Which is correct answer? Akhil, option A, modulating voltage. Or modulating voltage. FM carrier frequency deviation is determined by modulating voltage, modulating frequency, both modulating voltage and modulating frequency. Is there any confusion? Frequency deviation delta F is given by KF into AM. This is frequency deviation. So it is determined by modulating voltage only. But if the question is like this, in FM, the modulation index is determined by both modulating voltage and frequency. So in this case, frequency deviation is determined by modulating voltage only. Correct answer is option A, modulating voltage, because delta F is given by KF, a constant value, into amplitude of the modulating signal. So delta F is proportional to modulating amplitude. Okay. Beta is asked, then beta depends on both modulating voltage and frequency. Okay, right answer is option A, modulating voltage. Same question is asked for PM. Yes, for PM, it depends on modulating voltage and frequency. That is correct. Yeah, that is correct. In the case of PM, the carrier frequency deviation depends on modulating voltage and frequency. Yes, this is an important point. For PM, frequency deviation depends on both the modulating voltage and frequency. So we have discussed in comparison about this term, that is frequency deviation of PM is related to modulating voltage and frequency. Let's move on to second question. Which one of the following is not an advantage of FM over AM? When you compare FM and AM, Which one of the following is not an advantage of FM over AM? Yes, option B. Yeah, Sanjeev. Option B. Option B is lower bandwidth. Other options are, yes, Saurabh. Right answer. Option B is right answer. Other options are better noise immunity is provided. Option A is correct. Better noise immunity is provided in FM as compared with the AM. C, transmitted power is more useful, more useful, and D, less modulating power is required. All these options are advantages of FM over AM. Only this one, lower bandwidth is required, is not correct. Actually, FM require more bandwidth than AM. Right. Next question. FM broadcast extends from. FM broadcast extends from. Yes. Option D. 88 megahertz to 108 megahertz. Right answer. All of you got right answer. Okay, so you should remember this value, this range of frequency, 88 to, yes, Rakesh, answer is right, 88 megahertz to 108 megahertz. For AM, it is 535 to 1705, isn't it? Kilohertz. This is the frequency range for AM. Next question. Next question. An FM signal with the modulation index MF is passed through a frequency tripler. Frequency tripler. The modulation index of the output signal will be. Modulation index of the output signal will be. An FM signal with the carrier frequency FC and modulating frequency FC. Is FM signal with the modulating signal FM and the frequency deviation delta F is passed through a frequency tripler. Yes, option B. The trivial, your answer is right. Yes, 3MF. Frequency tripler means which will multiply the frequency by 3. Frequency tripler. So frequency will be multiplied if take carrier frequency FC. So both deviation in frequency and carrier frequency FC will be multiplied by 3 times. So we'll get a FM out with a deviation delta F. Since it is a frequency tripler, it will multiply frequency by 3. So delta F dash will be equal to 3 into delta F. So deviation of frequency will be multiplied at the same time. Center frequency FC is also multiplied by 3 times. So both the deviation and center frequency is multiplied by 3 times, but modulating frequency, which is not present in FM signal, will not be multiplied by this factor. Therefore, modulating frequency remains the same value. Modulation index, in this case, it is MF. MF is the modulation index. Modulation index or depth of modulation equal to delta F divided by FM. In this case, delta F dash is equal to 3 into delta F by FM. So that is equal to 3 into delta F by FM equal to modulation index of the original FM wave. So at the output, this FM wave has modulation index 3 into MF. Frequency tripler, multiply the frequency of incoming signal by 3. Frequency doubler doubles the frequency of input signal. It doubles the center frequency as well as the frequency deviation fc dash and delta fc delta f dash. Frequency deviation will also be multiplied by same factor. fc dash fc dash minus delta f, fc dash plus delta f. So it will be, deviation will be 3 times the original deviation. Therefore, modulation index is also multiplied by same factor. So correct option is option B, 3 mf. Next question. In commercial FM broadcasting, a radio station is transmitting signal 98.3 megahertz. It is option A, carrier frequency, option B, modulation frequency, option C, message frequency, option D, channel frequency. So which is correct option? In FM broadcast, frequency is not modulation frequency. D, channel frequency. No, it's not channel frequency. Yes, Chedna. Right answer is option A, carrier frequency. Channel frequency, actually channel is having a frequency range, frequency band. It is specified by the range of frequency. Channel is specified by a range of frequency, not a single frequency. Actually, a station is described by its carrier frequency. Right answer is carrier frequency, FC. Okay. And the modulated signal is for centered about FC. It will be extending from center frequency FC to a frequency range. This is the required bandwidth. Okay, FC minus delta F. We have already obtained the bandwidth. So center carrier frequency is the center frequency, which is denoted by the station frequency. 98.3 is carrier frequency. And the bandwidth extends, or channel frequency extends to both sides of this carrier frequency. Okay. So correct option is option A, carrier frequency. All of the radio stations have this carrier frequency as their meter or frequency. Next question, if in FM broadcast, the maximum modulation frequency is restricted to, maximum modulation frequency is restricted to, yes, Sanish, option C. Option C, yes, 15 kilohertz. 15 kilohertz is the right answer. 15 kilohertz is the right answer. FM broadcast, maximum modulating frequencies restricted to 15 kilohertz. Okay, next question. When modulating frequency is doubled, the modulation index is halved and the modulating voltage remains constant. When modulating frequency is doubled, modulation index is halved and the modulating voltage remains constant. So which is correct option? Yes, Chetna. Yeah, that's right answer. Option C is right answer. How did you get that answer? In case of FM modulation, FM system, modulation index beta is given by delta F divided by FM. Delta F KF into AM divided by FM. Modulating voltage remains constant. It is not changing. Frequency of the modulating signal, FM, is doubled. So what happens to beta when FM become FM dash equal to 2FM, AM remains constant value, then beta dash equal to KF into AM by FM dash, which is equal to KF into AM by 2FM. So modulation index become half the value, half beta. So beta dash equal to half beta. So modulation index become half the value when modulating frequency is doubled. So correct option is FM. Okay. I think it is clear. All of you should do the problems. Try to do all the problems. Next question is frequency modulation is advantages for option A, increase of signal to noise ratio without increasing transmitted power, easy suppression of certain forms of interference, avoiding the need for large amount of modulating power. All of these three. Correct option, yes. Right answer. All of you got right answer. So these are all advantages of FM. Increase of signal to noise ratio without increasing transmitted power, easy suppression of certain forms of interference. Interference in amplitude can be avoided in FM system by using amplitude limiters. Amplitude limiters are used in FM receivers to remove all amplitude variations. Amplitude limiters. So this forms of interference or noise can be suppressed very easily in FM system. Third point is avoiding the need for large amount of modulating power. Since modulating power remains a constant value, it does not need a large amount of modulating power. So correct option is all the above. So all of these are advantages of FM system. Next question. Amplitude limiters are used in FM receivers to option A, to eliminate amplitude modulation and amplitude modulated noise in received signal before detection. B, to eliminate amplitude modulated noise in received signal before detection. To eliminate amplitude modulation of received signal before detection to increase sensitivity of FM receiver. Option B. Amplitude received signal before detection. Okay. B is to eliminate amplitude modulated noise in received signal before detection to increase sensitivity of FM. So which one is correct? So all of you got different answers. Amplitude limiters are used in FM to eliminate amplitude modulated noise in received FM signal, received signal before detection. That's right answer. Actually, amplitude modulated noise is eliminated. Okay, there is no amplitude modulation taking place in FM, but we are transmitting it through the medium where due to interference of noise, there will be amplitude modulation because of noise. This is corrected by amplitude limiters. So correct option will be option B, to eliminate amplitude modulated noise in received signals before detection. So right answer is option B. Okay. Noise elimination, we are using amplitude limiters in FM system. Correct. Next question. Next question is a repeated question. The highest modulation frequency typically used in FM broadcast is? It is 15 kilohertz. Right answer. 15 kilohertz. So this question is repeated. Next question. Yes. Let us move on to next question. Here, the maximum deviation in FM system is 75 kilohertz, with the modulating signal being 10 kilohertz sinusoid. The bandwidth of above system is. Try to calculate bandwidth of FM system with the frequency deviation equal to 75 kilohertz and modulating signal is 10 kilohertz. Yes, Chetna, you got answer. Yes, frequency deviation and right answer is 170. Yes, right answer. Here frequency deviation and modulating signal frequency is given. Frequency deviation is denoted as delta F. Delta F equal to 75 kilohertz. Second quantity is FM, modulating signal frequency FM equal to 10 kilohertz. 10 kilohertz. So bandwidth is calculated using Carson's rule. Bandwidth equal to twice delta F plus FM. It's the formula for calculating bandwidth. Equal to 2 into delta F is 75 plus 10. 2 into 85 equal to 170 kilohertz. So right answer is 170 kilohertz. Okay, please check your answer. All of you, please check your answer. Bandwidth of FM is 2 into delta F plus FM. This is the formula used here. Okay, let's move on to next question. This question is having same data. The maximum deviation in FM system is 75 kilohertz with the modulating signal being 10 kilohertz sinusoid. If the modulating frequency is double to 20 kilohertz, yes, Chetna got answer. Yes, 20 kilohertz. The new bandwidth of the above system is modulating signal frequency is double to 20 kilohertz. And deviation remains same value. Deviation is 75 kilohertz. Yes, you got the answer. Right answer. In this case, only change is in FM. Yes, addition. Right answer. 190 kilohertz. Here, bandwidth is given by same formula. For FM, it is 2 into delta F plus FM. So try to do this question with the delta F equal to, is given as 75 kilohertz. And now the modulating frequency is doubled. Modulating frequency is doubled to 20 kilohertz. Deviation remains the same value. New bandwidth will be 2 into, substituting here 75 plus 20, you will get 95 into 2, 190 kilohertz. Means bandwidth varies with the modulating frequency. Modulating frequency is varied, bandwidth also varies. The correct answer is this one, 190 kilohertz. Okay, let us move on to next question. Same data is given. The maximum deviation in FM is 75 kilohertz with the modulating signal 10 kilohertz. If the modulating signal amplitude is doubled, the new bandwidth of the above system will be. In this question, frequency of modulating signal is 10 kilohertz, which remains constant value, but modulating signal amplitude is doubled. Modulating signal amplitude is doubled. So Harishnan says it is 320. The other one says 190. Which will be correct answer? What happens to the deviation if modulating signal amplitude is doubled? This quantity deviation, frequency deviation is given by, peak deviation is given by, so formula kf into am. When modulating signal amplitude is doubled, delta f becomes 2 times original value. Okay, so am is doubled. Am is doubled when modulating signal amplitude. Yes, right answer is right. Okay, correct answer. 320 kilohertz. When modulating signal amplitude is doubled, what happens to deviation? Delta f, and am is doubled, it becomes kf into 2 into am, isn't it? Equal to 2 into kf into am. That is 2 into 75. This is given as 75. So in this case, when we double the modulating signal amplitude, we'll get a frequency deviation of 150 kilohertz. 150 kilohertz. Therefore, bandwidth, new bandwidth is calculated with this delta f, 2 into delta f plus fm. Substituting here, we'll get 2 into 150 plus 10. 160 into 2 is 320 kilohertz. Right answer is option A, 320 kilohertz. So in this question, we have discussed the variation of different quantities and corresponding value of beta bandwidth is determined. Okay, I think this is clear for you. Yeah, yes, okay. Next, we are going to discuss about AM modulators. AM modulators, they are used for modulating analog information bearing signal, and information is obtained by varying the high frequency carrier. There are two types of AM modulators. One is square law modulator, and second modulator is a switching modulator or ring modulator. Square law modulator and ring modulator are two types of AM modulators. We will discuss on block diagram level of these circuits. Just moving to square law modulator. So square law modulator is a modulating circuit which employ a non-linear device. Okay, it's a non-linear device which will produce an output that is proportional to sum of input voltages, that is modulating signal and carrier. Let us denote this carrier by C of t, carrier. So modulating signal and carrier are applied in series to the non-linear device. Okay, non-linear device may be diode, BJT, or FET. You can use any of these devices as non-linear device because their output of non-linear device y of t can be written as a into a plus b into x of t plus c into x of t square, etc. If we apply x of t as input to a non-linear device, the output contains these terms. A constant term, b into x, a proportional term, and third term is proportional to square of the input. So this is nonlinear system which will produce an output that is proportional to a constant value proportional to modulating, input signal, proportional to, there will be a proportional term corresponding to square of the input term, and so on. So here, using this nonlinear device, we can obtain a signal which can be written as b into c of t, x of t plus c of t, okay, plus c into x of t plus c of t whole square, etc. We will omit higher power terms. And the square term especially contains a product term. We know that this product term contains x of t square, then a product term x of t into c of t plus c of t square term. Okay, so there will be so many terms in the output of a nonlinear device, and here we are using a filter circuit. Capacitor inductor combination is a filter circuit, or it is a tuned circuit which is tuned to frequency fc. So it will take only the frequency range near carrier frequency. It will take frequency components near carrier frequency. Okay, so the frequency range contains fc minus fm to fc plus fm, where the modulated AM signal lies. Okay, so this tuned circuit is tuned to carrier frequency, and the output of nonlinear device contains several frequency terms, and we are extracting the modulated signal, modulated AM signal, using this tuned circuit. Okay, so the output of tuned circuit contains AM signal only. That is how it is working. Actually, a nonlinear circuit or device will have an output which is which contain linear proportional terms, proportional to square term, proportional to cube term, etc. But we are extracting only the frequency range that we require. That is frequency range of AM wave. So which will contain unmodulated carrier having frequency fc, lower sideband having frequency fc minus fm, and upper sideband having frequency fc plus fm. So this tuned circuit will work as a band pass filter. Yes, it is given here, band pass filter, BPF. So band pass filter only allows a range of frequency between fc minus fm to fc minus fm to fc plus fm. So this is a tuned circuit. The transformer output, secondary of the transformer, will get only AM signal which contains carrier, LSB and USB. Okay, we are not mathematically dealing this circuit, only qualitatively analyzing it, how AM signal is generated. Okay, so there is no need of giving mathematical equations related to generation. Second one is a ring modulator. So ring modulator will produce a product of two signals. Ring modulator will produce product of two signals applied to it. First signal is AF, audio frequency modulating signal. Audio frequency modulating signal as well as RF carrier signal are applied to this ring modulator. So ring modulator circuit or switching modulator circuit consists of 4 diodes which acts as ideal switches. Okay, they acts like ideal switches. Therefore, the output obtained at the transformer secondary will be product of AM signal modulating signal, that is m of x of t. In this case, it is given as x of t, and carrier signal. So product of carrier signal and x of t will be produced here. Okay. So the product of carrier and message signal consists of only two side bands. Okay. Product of c of t into x of t, the product of modulating signal and carrier signal consists of two frequency components. They are FC plus FM frequency component, this is USB component, and FC minus FM frequency component, that is LSB component. So only two sidebands will be present. Carrier is absent in the case of ring modulator or switching modulator. So DSB out is the resulting waveform. We know that DSBSC does not consist of carrier wave. It contains only USB and LSB, right? So DSBSC is generated at the output of this type of modulator. So two types of modulators are, one using nonlinear device and the other using a ring modulator. Okay. These two are AM modulator circuits. Then similarly, we will discuss a block diagram level discussion on AM demodulators. Demodulators used for demodulating signal. Extracting modulating signal, original message signal can be extracted from modulated wave using demodulator circuit. So AM signal is applied to the demodulator circuit. Demodulator circuit will get a modulating signal. Modulating signal or message signal. So message signal is extracted from AM signal using AM demodulators. Here we are discussing two types of AM demodulators. One is square law demodulator. Second one is envelope detector. Envelope detector. Okay. First one is square law demodulator. Square law demodulator use a non-linear device, non-linear element like diode, BJT or FET as the non-linear device, and a low pass filter is used. So a square law device, AM wave is passed through a square law device, a property of which is already discussed. It will produce an output which is proportional to input signal, and there will be component proportional to square of the input signal. Now, when we filter out the output of the square law device using a low pass filter, here we are using a low pass filter to filter out the required message, low frequency baseband message signal. So message signal is filtered out by using a low pass filter in demodulator, square law demodulator circuit. The higher frequency components are eliminated using low pass filter. Okay, so we'll get only message signal which is low frequency. This is baseband signal. So baseband signal is separated using a low pass filter that corresponds to the message signal. Okay. In the case of AM wave, this type of envelope detector, we are using a rectifier. After rectification, it is passed through a low pass filter. So low pass filter will filter out the low frequency message signal. So message signal is recovered here, which is baseband signal. First, it is passed through a diode rectifier. Then, after rectification, the low frequency component is obtained at the output of low pass filter. Low frequency component is filtered out by low pass filter. The actual circuit consists of a diode and a resistor. So this diode will work as a rectifier. You can see the waveforms. Actual AM waveform is shown here on the left side of the picture. It is actual AM wave. AM input. AM input. Yes. After rectification, negative half cycle is deleted. Okay. Rectification is done by this diode. Only positive half cycle will appear. And positive half cycle is having an amplitude variation, which is slowly varying component frequency component of the signal. The slowly varying frequency component is separated out by low pass filter. So we'll get a variation which corresponds to the amplitude variation of the carrier pulses. Carrier pulses is having amplitude variation which is proportional to the amplitude instantaneous value of the modulating signal. Therefore, by using a low pass filter, we can filter out the low frequency component which corresponds to the instantaneous amplitude of the modulating signal. So here we have a low pass filter and a capacity filter also. So here we'll get a 1 by pi is a scaling factor occurring in this expression. So the output will be proportional to, if we write output as V0, it will be proportional to M of t. Okay, so V0 is proportional to M of t in this case. I hope you understood this working of this type of demodulator. This is a simple demodulator circuit using a diode and a low pass filter. Diode is working as a rectifier. The purpose of rectifier is to eliminate negative half cycles to get only positive pulses. After that, we'll use a low pass filter, which will produce the required modulating signal output, message signal output. I hope you got it. Okay. Yes. Okay. So AM not. Okay. Any doubt? You want to explain one more? You want to explain once more? Okay, I will explain. First stage is a rectifier stage. No. Okay, right. Depressed. How it is depressed? Yes. Actually, these pulses are high frequency component. These pulses are high frequency component. High frequency component. Okay, all of these carrier pulses are high frequency components. Okay, when we use a low pass filter will suppress the high frequency components. So output corresponding to high frequency components will be 0 at the output of low pass filter. So carrier pulses are suppressed. Only we'll get the variation, slow variation of amplitude of carrier pulses will be obtained. Since the power level of carrier pulses are suppressed, of course there will be a suppression in amplitude of the modulated signal.
But
right?
Sir, here only amplitude is suppressed. It shows that only amplitude is.
Just a minute,
It shows that. Yes, sir. Hello.
Okay. Now you can ask. Now you can ask.
Yes, sir. This diagram shows that only amplitude is suppressed, not a higher frequency.
Yeah, higher frequencies are suppressed. Actually, these pulses contains very high frequency components. These pulses means pulses are having very high frequency components, isn't it?
Okay.
What is meant by frequency? It is actually rate of change of signal, isn't it? High rate of change in signal is suppressed, means high pulses.
Means the power of.
Yeah,
means power only is the also, power of. power of frequencies are suppressed only,
No. Signal is
not
having both
frequencies.
different frequency signals are having different frequencies and power. Okay, when we suppress
Okay,
a particular frequency, that power is also suppressed. There is no doubt in
okay,
that. So here, these pulses contains higher frequency components and higher power. Okay, but the amplitude variation of the signal contains low frequency component and less power comparing with these pulses. So when we suppress a high frequency component pulses, the demodulated amplitude level will also will be less. Okay, right? It will contain a DC component as well as modulating signal component. Since we are using a uh, rectifier filter,
and what is the use of RC
then we
filter?
are using a capacitor to eliminate that DC level. You can see the difference between this pulse, this one and this one. And this one is having a DC level. It is above DC level. This is 0 volt level. And in order to restore the DC level to 0 value, we are using a capacitor which blocks DC, and the DC level of the signal comes to 0 volt level. So today's time is over. Actually, I want to discuss AM receivers also. Anyway, we can discuss it in next class. Thank you.